So this section is our first section to learn about how to solve a differential equation. So I'm going to show you how to solve a differential equation that is separable. So first, let's just start. It's separable if it can be written as dy dx equals g of x over h of y. If it can be written like this, basically another way we can cross multiply basically, and it can be written h of y dy equals d of x dx. We're just separating the differential. So you can see here, all we are doing is, can we get all the y's on one side and all the x's on the other? If you can do that, it's separable. So if we do separate all the y's on one side and x's on the other, all we have to do to solve this equation is integrate both sides. You see we already have our differential. And then what we get is capital H of y equals capital G of x. And instead of putting a plus c1 over here and a plus c over 2 over here, we'll just combine them and say plus c. First order, we only have one constant. So just in general, very simple process. You separate the variables, put all the y's on one side, x's on the other in this form. Integrate both sides and solve for y if possible. If we can't solve for it, then it'll just be an implicit solution. So we're going to solve the initial value problem where y of 1 is equal to 3 is our initial value. We'll be plugging that in at the end and solving for c just like we did in chapter 1. So first we're going to separate. Next, we will integrate both sides. Solve for y. I'm just going to reciprocate both sides. This is minus 1 over y equals and we can move this negative, take the negative of both sides and simplify. So one more thing we can do that I see, we have a 3c. C is a constant. It could be any real number. 3 is a real number. So we don't really need that 3 there. I call it, I say it gets absorbed into the constant. Okay, so we can basically rewrite this, instead of 3c, we can just use c. We don't need to use another constant. So this is called our general solution, right here. But this is an initial value problem, so we're going to solve for c. I think it was y of 1 is equal to 3. That was given right here. So that is my y of x. X is 1, y is 3. 3 equals. So for the particular solution, we just plug back in c equals 1 into there. And there we have it. Here's an example. We're going to find the family of solutions to dy dx equals ky. Recall this is, if you recognize this is from the last section in chapter 1, the exponential growth and decay, where if k is positive, it's exponential growth, and if k is negative, it's exponential decay. And what we did was we translated the rate of change. The rate of change is proportional to population, which is y is population, so ky is proportional. We're going to separate. Integrate. It's been a while, but what's the integral of 1 over y? Do you remember the derivative of natural log of y is 1 over y? So this is natural log of y. It's just a constant, so kx plus our c. All right. We want to solve for y. So if we want to get rid of natural log, we have to take e, do the inverse, okay? So e to the power of natural log of y is just plain old y. There's our goal. Recall a to the x plus y, that's equal to a to the x times a to the y. So this is basic exponential properties. If you have the same base, you add the exponents. Well, we have the exponents already being added, so we can basically say this is e to the kx, e to the c. We do this quite frequently in this class, so we need to be an expert at these exponential properties and logarithm properties too. So again, remember, just like that 3 got absorbed, e is a constant. So e to the c power is basically just a constant. That e can get absorbed. So we rewrite this as c, but I'm going to put it in the front. So c e to the kx, that gets absorbed. Some constant, we don't need to have an e to some constant. And so now this looks a little familiar, doesn't it? So I do have a question. Remember our original dy dx equals ky. So my question is, what about the solution y is equal to 0? If I plug this in to see if it's a solution, I take the derivative of both sides to plug in here. So dy dx is also equal to 0 from here. And then we get 0 equals k times 0. 0 equals 0. So y equals 0 is also a solution. That was not found in our family of solutions. So we call this a singular solution. And also a trivial solution. It has a couple different names. Because even though I plugged it in physically, I think we need to be able to see. If I look at y equals 0, I can just see this is 0 and this is 0. It's a solution. I'll put a check mark and say, yep, solution. So our final solutions are y equals c to the x and y equals 0, just to box them up. That's pretty much it for separable. I mean, I can do more problems, but it's basically just algebra. Move anything with an x on one side, y to the other, integrate, isolate y, done, unless it's an initial value problem.